hours to days, and light travel times. So essentially, the X-rays vary first. They interact with the disk, and then you see a change in the disk, and that difference is essentially the distance between the corona and the disk, wherever the interaction is taking place. And that could be hours to days in terms of light travel time. Right, so we're using light effectively as a ruler to measure everything around the AGN. Another way we can do this is we can do reverberation mapping on the reprocessed structures. So we can measure the time lag from different temperature regions. So we can look at the disk as thinking of it as different temperature sections and look at how, say, the X-rays or the hard UV vary, and then look at what the time lag is for the rest of the disk to vary. And so you could have either dissipation of gravitational potential, which is sort of flowing through the disk, and that's what's giving rise to the variations. And if you did that, then the luminosity in the disk is going essentially as the temperature of the fourth, and also this luminosity is going as essentially the accretion rate divided by the black hole mass divided by r to the third. So that's one way of doing it. And if you did this, then essentially, if you're thinking about the reprocessing is going as 1 over T, which is the differences in temperature in the disk. So then this lag would essentially go as you divide this by 4, or take the fourth root of that, and so you end up, the lag would sort of be proportional to wavelength to the 4/3 or so. You could also illuminate the disk from above, so you could have the corona being something like a point source or close to a point source in the center, and it's above the disk by some amount, and so it illuminates various portions of the disk from some scale height h. And it illuminates the disk. This also will go as h times r to the minus 3, so it again will have a sort of lag, sort of that scales with wavelength to the 4/3. You could also have intrinsic disk variations. And so then what this would mean is that the disk is varying first, and then the corona varies from that. So the corona is being powered by the disk photons, and so the disk varies, the corona varies, and then other things might vary. And so this has another prediction, and so you could think of a couple of different ways that the high energies could lag. One would be a long lag, so essentially you have this lag is tracing the Vissic's propagation timescale. For perturbations to reach the X-ray region from the optical disk. So perturbations have to reach up here somehow. And this might take a while. You also have a much shorter time scale, which is essentially the light travel time. So the UV photons, the seed photons, sort of traveling on the order of hours to days to the corona. And the corona is then upscattering those photons to the X-ray. In this case, basically you're talking about sort of illumination of a shell-like structure, and so it should go as r to the minus 2, and so the lag should go as wavelength squared or so. Just to give you an idea of the differences and where you potentially look for some physics here. So we can now do some monitoring, and I mentioned this was rather expensive, so typically people will sort of go all in on one object, and they'll observe it in every waveband they can. And so this was observed by Swift in various X-ray bands, and then in the optical and the UV. And so you can see sort of the variations in the UV in particular. This is about, I think, 2,000 angstroms or so. So it's not super far UV, but it's reasonable. And so you can see there's pretty good correlation here. If you look at the X-rays and essentially go from the 2 to 5 keV ones, you see the peak, and so everything is going to be measured from this peak, and so you see the lag with itself is 0, and the lag with this is maybe slightly negative. So the hard X-rays are varying first, and then the soft X-rays, and then you see essentially the disk is moving out in terms of time lag. So the X-rays are preceding. The variation in the X-rays is preceding the variation in the disk. And so this suggests that you're having some X-rays coming from the corona, which are raining down on the disk, and you're reprocessing, essentially reflecting those X-rays, and that's leading to this lag here. But you don't see it sort of continue out. It sort of continues out to here, and then it kind of is even, or so. So you can look at this time delay versus the wavelength, and essentially you can map out something like this. So this is the sort of strong correlation that I was showing in the previous slide between the X-rays and the hard UV or the far UV. And so the X-rays and the UV are reasonably well correlated, but if you were to extend this, you would extend this in sort of this line here, and you wouldn't follow the optical portion. So there's like a sort of a disconnect between the UV and the optical disc somehow. And so this correlation doesn't track out to the edge, the further portions of the disc in the same way. And then the other thing is that the optical UV, as I said, lags behind the X-rays substantially. And there's a pretty uniform sort of lag here, but the slope of it's different. And so you can fit this with different disk models, for instance, and different sort of illumination structures. But you'll notice that this dotted line here is the beta 4/3. So that's the wavelength goes as to the 4/3 power. And so that actually fits pretty good. And so we're thinking then that if we go back to here, that either we're seeing dissipation in the potential, but the problem with that is potentially that the X-rays probably wouldn't drive this dissipation, right? The disk would probably behave by itself, maybe. And so the illumination from a point source seems like a more likely scenario because that point source is the X-rays sitting above the disk, and it's preceding the lag in the UV. So we can actually kind of get a physical idea of what this, the corona, the reason we even called it a corona and where it sits and everything comes from studies like this, where we can actually figure out what the distance is and look at the geometry of things. There are also relativistic effects that come into play here that I'm not going into at all, but they create some of this process as well, in terms of focusing the X-rays on the inner portion of the disk or the outer portion of the disk, only having reprocessing going one way and not the other. So you can now sort of think of this picture. We start with the corona, which is giving rise to the hard X-rays. Then you have something which is giving rise to the soft X-rays and the far UV. And so it turns out that in the X-ray spectra of mini-AGN, you see a soft excess. And this soft excess is thought to be relativistically blurred. And so if it's relativistically blurred, you know that it has to be pretty close to the black hole. It's feeling the potential rather strongly to get the effects of GR. And so it's relative, whatever is producing this soft excess is very, very close to the black hole. So we think it's potentially related to the inner portion of the accretion disk in some way. So this creates the far UV and the X-rays, and so all of this then illuminates the disk, illuminates the broadline clouds, illuminates the torus, illuminates the narrow line clouds further out. So that's the sort of structure that we have for this reprocessing. So one very interesting thing is, so in this picture you have this disk and you have these broadline clouds. So what's going on here is that you have, it's even if you didn't have the AGN, you still have clouds going around the galactic center. They may be fewer, less dense, et cetera, but you can imagine that through centripetal sort of angular momentum, they're going to mostly make a disk, but they will have some objects which are sort of higher, some clouds which are higher, and they're just moving around in sort of Keplerian orbits. As you go closer, they'll move faster, right? And so we can imagine these individual clouds, something like this. You turn the AGN on, and you're going to have some ionization structure through it. So essentially, when you have variations here, those variations are going to propagate out on roughly the light time travel scale out to these clouds. You'll see some variation there. And so measuring that variation automatically places the clouds in a certain distance from the AGN, right? For a given black hole. Yes? Yeah.
No, nothing.
Well, so I'll get there. Right, so the idea is that you have these clouds floating around, and probably the torus is these clouds too, but the issue here is that this line represents the dust sublimation radius, and so interior to this, all the clouds will lose most of their dust, not quite all of it because there'll be some shielding, but outside of that, you'll have clouds with all sorts of dust particles and molecules and so forth. And so this is probably just an extension of this, but with dust as well. And whatever dust effects also happen. But we are lazy and we just call it a torus, but really it's a collection of clouds. Probably all of this is kind of shredded molecular clouds that are funneling in. In here, these clouds might also be from the disk. So you might imagine that the disk has some radiation pressure, and so it pushes up material. And that material, which was from the disk originally, ends up forming in these clouds somehow. So that's another possibility. And so the interaction between the disk, the torus, and the clouds is not really well constrained because it's very difficult to actually, we can't resolve it very well. So we're just interpreting everything from the time lags, mostly. So we have this disk which is illuminating UV. We have the soft excess, which is hard UV and X-rays. And that radiation is incident on these clouds. And so light travel time might take several days to up to a month, depending on where the cloud is, if it's close or far. And the changes will potentially be dramatic when the AGN is varying. And so bigger AGN, bigger mass black holes, will vary less than lower mass black holes. You'll see the variations easier in lower mass black holes than in bigger mass black holes. So the photons hit this cloud, and they're not going to instantly make it all the same, right? But you're going to have sort of a sort of different ionization structure throughout it. And so the edge of it will be pretty strongly ionized. So you'll have essentially protons and electrons here. You'll have some helium-2. And then further in, you'll be a little bit shielded, so you'll still have some neutral hydrogen. But you can also have ionizing, you can ionize some other elements as well that might have a lower potential. And so each cloud might have this structure. And then you can also imagine that depending on where the cloud sits, it will see somewhat different UV radiation field, right? Because as the UV photons propagate out, they're going to be intercepted by material, and so you'll pick off some of the harder UV photons, and so the spectrum will change as you go out in distance a little bit. So these clouds here will not necessarily see the same radiation field as these clouds here. And so these clouds generally, you end up seeing a harder UV field, and so you get sort of, you strip off more of the electrons from the gas, and you end up seeing higher ionization species. So helium-2, nitrogen-5, et cetera. And those tend to come from this inner portion of the broad line region, whereas something like hydrogen might actually come from more out here, be dominated more from the outer portions. And so this is what this difference between UV optical and optical is just that the species will actually change a bit over this distance. If you think about this individual cloud and you run Cloudy through it, which is a sort of ionization equilibrium modeling software, you can end up seeing this distance is not really anything, it's just the distance, it's a normalized distance through the cloud. But what you see is that there's some weird ionization structure here. So H alpha, you can see that essentially the emissivity sort of peaks here, flattens off, and then has a very strong peak over here, and then flattens off again as you go through this portion of it. And you can also see a similar thing for helium-1, which is in yellow. Lyman alpha is more sort of emitted just in this portion and not in this portion. And then you also have helium-2, which is a high ionization species, which is just emitted sort of at the front of this. And so as you place this cloud at different portions, you'll have a different ionization sort of structure for this. And what this ends up meaning is that most of the emissivity of hydrogen is coming from out here. Most of the emissivity from helium-2 is coming in here. They're at different radii, therefore they're at different velocities. And so the widths of their lines will be different. And also the lag, the time lag between them will be different, right? Because you'll see a time lag first with helium-2 before hydrogen, if there's a variation in the disk or in the corona. So this is actually useful. Because we can use light as, again, a ruler. And so we can start to map out this structure in great detail. Okay, so the broadline region is essentially less than 1 month, one light month across for a typical Seyfert galaxy AGN. In many of the cases, I'm showing NGC 5548 because this thing was studied to death back in the 80s and 90s and continued to be studied up till a few years ago. So this is from one of the early monitoring programs, and so just looking at the variations in all of the different lines, so the UV continuum, the optical continuum, helium-2, Lyman alpha, H beta, et cetera. And so essentially you see that the UV flux varies first, little lag of a few days with the optical, and then most of these sort of move out from there. And so the H beta is actually about 20 light days out. And so if you saw a variation in the UV, you could wait 20 days and you will end up seeing the variation in H beta as those particular clouds are reacting. And so in this picture, slightly different picture, but you have the sort of black hole, the disk here, and the broadline clouds. And so the helium-2 clouds are kind of mapping this portion of the disk, the helium-1, this portion, the Balmer H beta, this portion. And so you'll see the time lag differently for them as seen here, and you can map that out in terms of this is light days, this is the velocity width, and you can actually see that this matches pretty well with a Keplerian model. So it's pretty nice and sort of consistent, easy math. Okay, this brings us to an interesting point. So we can actually use this technique, which is called reverberation mapping, to constrain the system. So we can actually put tight constraints on the broadline kinematics and the geometry by looking at the response of the emission lines to the continuum changes. Because it's a simple time delay. We're waiting for light to propagate, and we know the speed of light, so we measure the distance. So if these broadline kinematics are essentially dominated by the potential of the black hole, which we think they are, we can essentially derive a virial estimate of the central mass using the time lag and the broadline width. And so the black hole mass is essentially related to the velocity and the radius and this F factor here, which is sort of just a scaling factor, which is related to the accretion rate. And so R is just delta T times C, right? Light travel time. And the velocity is just the width of H beta, assuming it's in Keplerian motion. And so you measure these two things, and you get a black hole mass. Pretty nice. In addition to doing this with H beta, you can do this with all the lines, and you'll get different distances. You have different velocity widths, and so hopefully the black holes agree in all those cases, and generally they do. This has been carried out for something like a few hundred low luminosity Seyfert galaxies and QSOs over the last 20 years. And people are trying to map out a larger fraction of black hole parameter space. At the start, it was kind of just the low mass black holes because they varied faster. And so you could actually do it on human timescales. For some of the high redshift, really massive objects, one, you have, because the black hole is bigger, the variations are smaller, and then because they're also at high redshift, you get a time lag from the time travel through Hubble time, and so you have to wait maybe something like 10 years to see this reverberation in some of these objects. So it's a big project. It's more than a PhD. You have to be really dedicated for a significant portion of your life to do these type of projects. So it's tough. So that's why there's relatively few. The problem with that is that if you don't map out all the black hole parameter space, what you're doing then is using this relation for local AGN and extrapolating it 4 orders of magnitude and hoping it still applies to 10 to the 9 solar mass black holes. And that may be dangerous. In general, the mass estimates from this technique are typically good to about a factor of 3, although there are lots of uncertainties, lots of assumptions and biases in there. But the ones that are actually estimated with the reverberation mapping, the masses are typically, they're probably quoted to better than a factor of 3, but with the systematics, they're probably a factor of 3. Okay. This is just showing the black hole mass versus the sigma, which is essentially the full width half max. And you can see this nice relation here, which is just demonstrating this. This slope is very close to 0.5, which is what you would kind of expect from a Keplerian sort of solution. So this is an interesting technique. You can also look at the broadline region size, and that's correlated with the AGN luminosity. So you can measure this for multiple objects, and you get essentially this broadline size, where the broadline sits, or where the H beta emitting region sits, versus the luminosity. You see a nice relation here. And so what this does then is provide a very quick and easy way to estimate black hole masses. Essentially, if you have the luminosity, you know the radius of the broadline region for that particular black hole. If you know the radius and you measure the full width half maximum, you have the black hole mass. Now those two things, the luminosity and the full width half max of H beta, you can get in one spectrum. And so you calibrated this, right? You made sure it worked, and now you can take a spectrum of an object and measure its black hole mass. That's very powerful. And so you can now do this, and so black hole mass essentially is related to the luminosity and the full width half max in something like this relation in terms of solar masses. And so again, this is just showing the same thing, this correlation. And so you have black hole mass versus optical luminosity, pretty reasonable correlation. And so you can now go out and apply that to Sloan, which observed 100,000 AGN, and you now have black hole masses for all of them, right? And that's a lot of statistics. Maybe you can't trust them fully because you're applying this in a regime. Most of your sources had black hole masses at 10 to the 7, 10 to the 6, and maybe you're applying them up here. Maybe that's not so great, but it's something, right? You can start to do stuff with that. This is the full width half maximum constraints. You know that there's probably a selection bias here, so we're just not sensitive to these objects because they're too faint. And you can look at the luminosity versus the black hole mass. You can see that there's this essentially a bias there, but from the survey. But it's interesting. So the broad lines are essentially a proxy for the black hole mass. And this is one of the most fundamental important things we've been able to sort of discover in the last 20, 30 years. The most massive black hole known is this guy here, OJ287, black hole mass of something like 2 times 10 to the 10 solar masses. I think this might be old. I think there's probably another one now that's almost 10 to the 11. So then the question is, how do you actually make a black hole that essentially has the same mass as all the stars in the Milky Way? Maybe that's not trivial. But we'll come to that question later. Okay, so some other correlations. So if we look at the UV radiation versus the X-ray radiation, we find a correlation. That's maybe not too surprising. You know, they're pretty close. They're within a light day or so of each other, and you might expect there to be a lot of interplay. And so, you know, as you scale up the accretion, you might scale them both up, and they might relate. So they do, and you can divide them. So this is just looking at the line here, and so you can see that essentially the slope is not quite linear. depending on what sort of you apply here. But essentially, it's not one, right? So there's not a one-to-one relation between them. And so we can measure the ratio of these two things as a slope. So the slope between the X-ray and the optical, and we call that alpha OX. And we can compare alpha OX versus luminosity, either the optical luminosity or the X-ray luminosity, and you see that there's a nonlinear correlation here. It's linear, but it's not uniform, or it's not one. So there's a change in alpha OX with luminosity. And this, we can imagine this might come into play because we saw that there was some changes in the UV with accretion rate. We saw that there were definitely some changes in the X-ray slope with accretion rate. And so we could imagine that that's sort of driving this. But it's, the dispersion here is about maybe 0.1, 0.2 over 1, 2, 3, 4, 5 orders of magnitude, which is that's a pretty good correlation. So this is pretty important. We're not sure if it's necessarily driven by the black hole mass or the accretion rate, but essentially, it's tracing something about the inner disk. That's interesting. This is another version of that, now using many thousands of AGN, where you have X-ray data and UV data. What's interesting about this is, so there is some scatter here, but because this is nonlinear, we can go out and measure the redshift of this object, of each object, get a distance, get a luminosity, but we also can measure the alpha OX, and the alpha OX tells us essentially the luminosity, right? It's a one-to-one sort of correspondence. You measure alpha OX and you get a luminosity. We have two measures of the luminosity, and that allows us to estimate essentially the Hubble expansion. And so we can actually use quasars as a standard candle, or a standardizable candle. There's a decent amount of dispersion in the alpha OX relation, and so this is the individual measurements, but we have many, many thousands, and eventually we're going to have 10 to the 5 of these things once eROSITA launches and observes. eROSITA is launching next month, and it's going to observe over 4 years and end up with almost sort of 250,000 AGN that are observed in the X-rays and in the optical. And so you can beat down all of this noise here with statistics. And so if you average these, you get this red point here. And you can already see that the red points are in pretty good agreement with the standard model. And in very good agreement with the supernova, which only go out to redshift 1.4. The benefit is quasars are on all the time, right? Or at least for our intents and purposes, we see them and they're on. They don't disappear the next day. So we don't have to rush to get an observation of them like supernova. We can see them out to the edge of the universe, or the edge of the observable universe, right? So out to redshift 6, at least 7, 7.5 is the highest one. And so these are very interesting because they're probing a regime that we can't probe with supernova. And so we can compare these with the measurements from Planck and so forth. And so we're starting to be able to use AGN as standard candles in this sense, which makes them very interesting and makes trying to understand their systematics sort of imperative, because we want to beat down this error here and try and really get a very fine measurement of this to do essentially cosmological, sort of precision cosmology. Okay, other relations. So most of the luminosities correlate with each other. You have the X-rays and the UV. We already saw that they correlated, but we also have the dust beyond the dust sublimation radius, and that is just receiving the incident amount of radiation and re-radiating it. There's a little bit of difference depending on the orientation, and so there's maybe a factor of 2 or so. Sorry, this is a bit small, but there's essentially a factor of 2 depending on the orientation. And so this drives, where is this plot? Here, let's see, 6 micron. Yeah, 6 micron versus X-ray versus 6 micron. And so you can see there's some dispersion here. And so that dispersion is largely due to orientation effects, because there's anisotropy in the amount of radiation that the torus is giving, or the clouds are giving. But nonetheless, it's a pretty decent sort of correlation with a bit of noise. If you really pinpoint it down with better precision, this is not very, these are Spitzer data, but if you actually get very high resolution, spatial resolution data, you can see that the correlation is very strong between the X-rays and the 6 micron. And so, again, that's essentially measuring a distance of the sublimation radius. So the dust sublimation radius depends on the central engine luminosity, effectively. You can play a similar game with the narrow line region, so the oxygen 3 lines, the nitrogen 2 lines, et cetera. And those also are effectively just seeing the incident radiation and scaling from them with some sort of factor based on the covering fraction of clouds on the sky, or seen by the AGN. And so those both trace the central engine. So that's why there's this correlation. What's interesting about the 6 micron in particular is that you can actually, again, use this as a standard candle. So you have, again, the distance from the spectrum and the luminosity from the spectrum. You can measure the sublimation radius from the time lag in the near infrared. And so you essentially wait for the AGN to vary. You wait for the near infrared to vary. The near infrared is tracing the edge of the sublimation radius. And you then have a distance. And you can use this, again, to sort of, do a distance modulus versus redshift. And the errors are much better here. The data are, it's much more expensive to do this, but the errors are very good, and actually you see, again, very good agreement. The benefit of both of these techniques is that they have completely different systematics than the supernova. And so you can, come at the problem from different ways and try and narrow down the sort of banana wedge that constrains cosmological parameters. Another fundamental relation is the fundamental plane. This is a relation between the radio emission in the core, and the disk emission, traced by the X-rays or by the UV. And so this generally was seen for low luminosity AGN and some AGN, and then actually extended to stellar mass black holes. And yes. That tells me I have 10 minutes left. Okay. And we see some sort of correlation. It's not clear exactly what's going on here between sort of quasars and these sort of other quasars up here. But there's, this is, again, over 10 orders of magnitude. And so there's something there. But why it exists is less clear. So again, it's an active area of study. Okay. Then the final relation we have is essentially taking the black hole masses and relating them to the host galaxies. And so, essentially, this was a huge project that sort of came about even before reverberation mapping had really nailed down the black hole masses. And so people were trying to do it in the nearest objects, trying to resolve the gravitational potential and look at the dynamics and then compare that with the host galaxies. And so dynamical searches for the nearest objects, and so these are all NGC numbers or Messier numbers, essentially come away with black hole masses that are of the order of 10 to the 6 to 10 to the 9 for these galaxies. And fairly robust sort of estimates of this. And so this is kind of what they do. So you can look at the velocity dispersion, you can look at the velocity, you see a nice sort of rotation curve here. This is for MA31, and you can see that the black hole is, this massive object here is changing the potential, and we can measure that. We can resolve it. And the dispersion goes up, and you can measure the mass. And it has a mass sort of somewhat similar to the Milky Way, many times 10 to the 6. You can, again, do it like this, and so you can look at the mass to light ratios. You can compare. So here the mass to light ratio increases quite dramatically. Remember from the early arguments we had measured a mass to light ratio of 25 for some of these galaxies. And so here now you can see that the mass to light ratio is going up to many hundreds, thousands, because we have better data. And so we have the velocity of a massive object, and we have a huge mass to light ratio suggesting a dark object, right? Not a normal stellar object. So again, you can measure the mass-to-light ratios, et cetera. And so you can get the black hole masses from these kinematic estimates, and you can compare them to the bulge luminosity, and you see a nice correlation. The bulge luminosity is just tracing the stars, so it's effectively tracing the mass. And so we see that there's this potential correlation with our galaxy, M31 here, a few smaller galaxies, and M87 up here. This is again sort of doing this with a few more objects, and so you start to see that the correlation is coming into play. This is sort of known colloquially as the Magorian relation because Magorian was one of the first people to sort of publish this. Laura Farisi also worked in this, looking at the velocity dispersion versus the black hole mass from these early studies. Again, black hole mass versus luminosity of the bulge or this dispersion, and you see that there's a better correlation with the dispersion than with the luminosity, and so the dispersion is the main sort of driver there, and this is the dispersion of the bulge. And so here's a more updated work from 2009 from Gludekin, and showing the different methods to get black hole masses here, the different types of galaxies, and the errors on them. Mostly errors in black hole mass, not so much in dispersion. And so you can come away with a relation for the black hole mass given this velocity dispersion, which is pretty reasonable. There are a few sort of outliers here, and so it's sort of interesting to understand why they're outlying this relation. One of the things that is sort of difficult, you need to measure the dynamics of the stars. And so in this case, you don't want the AGN to be on, because the AGN will blur all, it'll dominate and contaminate that emission. And so most of these have been done with quiescent galaxies, inactive galaxies. And so it's sort of tricky to then take the black hole mass estimates that we have for active galaxies from broad lines and try and marry these into the ones done from stellar dispersion. But people have started to do it. Let's see, this is just the elliptical and S0 galaxies, and you can see there's a bit of dispersion here versus this one. So again, a slightly different relation. Okay, and so this relation is kind of interesting because you have the black hole is related to the galaxy mass, essentially, the bulge mass, and the normalization is essentially a factor of 1,000, which was very similar to the factor of 1,000 that we had for our own galaxy that we talked about yesterday. And so how does this come into place? How do you lock in the black hole mass to know exactly how big the bulge is? Right? The black hole is existing in a tiny little area. The bulge is essentially a large fraction of the galaxy, or a sizable fraction of the galaxy. And how do they know about each other? That's sort of tricky. The scales are many orders of magnitude, 10 orders of magnitude at least. So how do they know about each other? So people started doing simulations, and they were doing simulations of galaxies, trying to recreate the observables in the local universe. So they had dark matter simulation. They would populate them with some test particles and see how they sort of merged. And one of the things that came away with that was that, in general, they produced too much star formation. They continued to produce stars. And so they needed some way of stopping the star formation from happening. In particular, the cold gas was, gas was accreting into the center, cooling down, making lots of stars. And so the central portions of galaxies tended to be bluer in the simulations than in real life. And so they needed something to stop that star formation. And so they ended up putting in feedback, initially from supernovae, but that wasn't enough. And so they needed something else. And so they invoked AGN. And so we've already seen that some AGN have jets. Other AGN have winds. We'll see in a little bit. And so they kind of just put that energy in the center, and they said, okay, the gas is going to heat up. Done. And so they made some simulations, and this is kind of what this looks like. So you have a galaxy merger. As it's merging, the yellow is this feedback effect, and what it ends up doing is heating the gas, blowing the gas out, stopping star formation relatively rapidly, and so then the galaxies evolve passively and turn into the wonderful big elliptical galaxies that we see in the local universe today, which we call red and dead because they've stopped forming lots of new stars. So this feedback, essentially, what this will do is it will lock in this relation of black hole mass and sigma. And so as you accrete more gas onto the system, it's forming stars, and some of that gas is flowing down to the black hole, accreting onto the black hole. And with reasonable assumptions, you can kind of come away with something that looks like the correlation from the simulation. And so that was pretty successful in sort of saying, okay, we can do that. It may not be fundamental in sort of understanding the physics of how you get the gas to the center and so forth, but it seems that it just kind of comes out naturally. This is just looking at the star formation rate versus time. And so without the AGN, you see that the star formation kind of plateaus off, whereas with the AGN, it dies down relatively rapidly, and this allows for red and dead elliptical galaxies. So what evidence do we actually have for feedback? The feedback was really invoked on a need from the simulations more than from observables. We observed some feedback, but we haven't had a connection between the feedback and actually stopping star formation in its tracks. We still haven't. I mean, this was in 2005 when they published this, and people have been looking for it for 15 years, and we see some evidence of it, but it's not ubiquitous. It's not everywhere. So what evidence do we actually have? So if we look in the centers of local galaxies, Seyfert galaxies, we see that they have these ionization cones, which are being illuminated by the AGN, and we can measure the velocities. And actually, that ionization cone is a wind coming off of, seems to be a wind coming off of the AGN. And so you could imagine that this wind might impact with some molecular clouds and maybe shreds the molecular clouds so it stops star formation. You can make calculations of this, and it turns out that, well, a lot of this wind is going in a direction that's not really useful for the galaxy stopping star formation, because the star formation is occurring here, and the wind is kind of going perpendicular in the path of least resistance. And so that plus the energetics make it a little bit difficult to stop star formation in kind of local spiral galaxies. And so again, here you see another sort of portion where we're zooming in with the radio jets, and we see radio jets that are kind of in here as well, providing a mechanical energy. So this was a radiative energy. This is a mechanical energy, but it's also, again, very collimated. And so it wasn't clear exactly how you might have energy in one particular direction, but how do you sort of distribute that in a way that will actually stop the stars and gas from cooling down, or sorry, the gas from cooling down and forming in stars. So we have two types of potential mechanisms. One is this radiation-driven wind. And so essentially, the effect of a protogalactic wind may be estimated as follows. We have an isothermal sphere with a gas fraction that's assumed here, and constant velocity dispersion, and a mass, something like this. And a sufficient intense wind from a central quasar can sweep up the gas into a shell and push it outwards with a constant velocity, which ends up being related to the Eddington luminosity and the gas filling factor and the dispersion. And so essentially we can end up having, so for a luminosity, an Eddington luminosity of something like this, we can end up having a mass outflow which is sort of modest. And so this allows you to move out some mass, but not a whole lot. Likewise, you can have momentum-driven outflows. These essentially come from radio jets, and there you can actually drive a lot of momentum, but it's very much collimated. And so again, you can end up sort of, a black hole will sort of drive a certain amount of mass outward. what evidence do we actually have that this works? So in the X-rays, we see these, in a couple cases, these very broad absorption features. And these are thought to be ultra-fast outflows, or UFOs, as they're called. And so essentially those are outflows moving at a fraction of the speed of light, very close to the AGN, and potentially carrying a lot of momentum with them. And we can calculate what this momentum is, and it can drive out several stellar masses per year in sort of some of the extreme cases. That's not a whole lot. This is the sort of UFOs and sort of the blue shifts in terms of their velocities. You can see, well, most of the UFOs are greater than 0.05 C, and they go out, we've measured some that go out as fast as 0.3 C. We also have optical observations with IFUs, and here you have a QSO, you have, this is Markarian 231, and you can see that the velocity dispersion close to the black hole is pretty high in terms of, well, this is, I think, this is net velocity, but essentially this sort of velocity, we can go here, let's see, oh, I don't have it. Anyway, this should have a dispersion of about 800 kilometers per second. In most of the directions, with a little faster in the jet direction of about 1,200 kilometers a second. And so this, actually, this is a ULIRG, and so this was two galaxies that clashed together. They were forming lots of stars, but the AGN is now starting to sort of carve out and stop the gas from actually forming stars in the very central region. And so here, I think the ability is to potentially drive out something like 10 to 50 solar masses per year in terms of actual mass. So again, not a huge amount, but it may be enough to potentially stop the star formation, which is of the order of 50 solar masses per year as well. So it's kind of getting there. Okay, let's see. There's a couple of sort of oddities with this sort of black hole versus bulge mass. You see most objects are here, but there are a few objects which are off from it. And so we need to explain why those objects would be off. Why either the bulge formed a lot more mass than the black hole, or in a couple cases, why the black hole formed a lot more mass than the bulge. And so that's a little bit difficult at the moment. Yeah, this is in particular one object which is pretty well sort of constrained and sits way up here. So it has a big black hole compared to its bulge. Okay, there are also other biases because essentially we don't observe the sources down here, and so we estimate a relation which is like this if we don't take into account the biases. So this is just sort of showing that. And then finally we have these two sort of feedback modes, and this is sort of in terms of an evolutionary scenario. And so in this sort of scenario, the radiation-driven scenario, you have radioquiet quasar, which drives a wind, and that essentially pushes out over time. In the radio scenario, you have a sort of hotter halo, and you accrete gas more slowly, and the jets turn on every so often, and heat up the halo, and then they turn off again. And so, we might see the jets in only a few, one in a few 10,000 objects, and so they turn on relatively rarely, but they're enough to sort of heat this outer region enough so that the gas stops cooling and forming new stars. Okay. Let's see. So some more evidence. This is essentially just looking at, again, winds that are been driven off of very close to the AGN, probably off of the disk of the AGN, and so this is in terms of light days. Seeing velocities up to sort of 6,000 kilometers per second or so. Let's see, I'm going to skip through all that. Just more evidence of different winds out to high redshift. And I wanted to get to, let's see, no, I'm just showing it again. Okay, so a couple of interesting objects are these. So again, in Markarian 231, we saw with the IFU observations, we could move out neutral material and ionized material. And when we looked in the submillimeter, we actually were able to measure the CO. And the CO has this broad wing as well. And so we think that the AGN is able to actually move out the molecular material with velocities up to sort of 500 or 600 kilometers a second. How this is done is not really understood. It probably means that the molecular gas has to form in situ, because if you take a molecular cloud and you try to drive it up to 500 kilometers per second, it completely shreds. And so probably the gas was moving and then started cooling as it was moving out. And we're starting to trace that. So there's lots of studies coming with IFUs and with Alma that are trying to sort of constrain this better. We also see molecular gas from Herschel, looking at the OH absorption lines, which are being driven out by, again, sort of 500, 600 kilometers per second or so in some cases. And this seems to be a function of the AGN luminosity. So the maximum velocity is driven by the maximum sort of velocity or maximum luminosity of the AGN. Okay, finally, clusters of galaxies are sort of an interesting situation. So clusters of galaxies, you have many old sort of red and dead objects. You have a hot halo of gas, which emits in the X-ray, which is sort of shown by this blue halo here. And there was a typical problem here where this gas was thought to be able to cool on times shorter than a Hubble time in the center. And so you should see a lot of gas cooling onto the central object and forming lots of stars. But we don't see that. This was known as the cooling flow problem, or the entropy floor problem. And what we needed was essentially some way of heating that gas up. And so again, people turned to AGN feedback. And what was interesting is that we took images with Chandra, and this is what the Perseus galaxy looks like with Chandra. This is what it looks like in the optical. This is what it looks like in the radio. And if you match the radio up here, you'll see that it matches pretty well with these holes in the gas. So the radio is essentially moving out cool bubbles of gas within this hotter gas that's emitting in the X-ray. And if you do unsharp mask images, you can see the bubble in better detail. So you remove the smooth components and just look at the features. And you see actually lots of different shock fronts. And so the idea is that the radio jet is moving this bubble out, and these bubbles are kind of buoyant, and they move through the cluster gas and heat it up, or sort of transfer and homogenize it a bit. But you also see older bubbles, ghost cavities, out here. So this radio sort of feedback was cyclical and is able to heat up the cluster and stop this gas from cooling into the central bright cluster galaxy. So this is a sort of interesting way that feedback is actually affecting scales that are now way beyond the galaxy. Right? This is 1 megaparsec in size. Or so, actually, not 1 megaparsec. This is 40 kiloparsecs, so half a megaparsec in size, something like that. So that's really pretty impressive, right? This black hole, which is sitting down in essentially something like the solar system in terms of size, is able to affect the entire cluster of galaxies. Okay, so that's where I'll end. Well, that's where I'll end. And take any questions.
So you talked about the reverberation mapping.
Yeah.
So we can use this for high Z quasars because the
light travel
for
time.
the light to travel.
Yeah.
So what is the maximum Z we can use for this study? Approximately.
It depends. So, I mean, essentially going to redshift 7, the time lag will be 7 times longer, right? So it's not a huge difference, but mostly we can see very massive quasars at high redshift, and so they're going to vary less. So we need very, very fine measurements if we're going to measure them, and then we have to wait essentially the lifetime of LSST maybe to get a reasonable sample. That being said, we've observed some quasars and they varied on faster timescales. And so they varied on the timescales that we've we've looked on them, so months to year. So it may not be that bad. For waiting for the light to actually hit the broad lines and things like that to calibrate, maybe that's not what we want to do, unless we really need to do that. We might have closer objects that are massive and we can do the same thing. But it's possible.
But that data you used was for what redshift?
Well, so most of the reverberation mapping projects, the lower mass black holes were done locally, and then higher mass black holes, typically they went to somewhat higher redshift and had to wait for longer periods of time.
Mm-hmm.
But they've published calibrations for that at this point, and they're starting to publish some more as they build up a bigger sample. But they've been doing it for 20 years at this point. So they're starting to have a decent sample.
Hi. Couldn't the Cielo QSOs have changed their orientation and now we are looking at different places? Kind of, before we are looking to the flux of the broadline regions, and now somehow they have changed the orientation that we are looking for, and now we are looking at the torus or the narrow line, and this is the cause of the change we are looking.
Well, so that has to happen on a dynamical time scale. And so, you're talking about either the entire galaxy moving or something moving in the way and blocking it. And both of those things, dynamical time scale is sort of probably moving the torus would probably be 10 to the 6 years. And we're seeing these variations on 10-year scales. Actually, there's some cases where we've seen them on, I think, less than a year scale, which is really sort of pushing it in terms of how fast things are changing.
All right, thanks. And in the last picture, you showed the cluster, the other one.
This one?
The
Or
cluster,
no.
Can be the one.
This one.
The cluster feedback, right?
Yeah.
In that picture, the radio jet is perpendicular to the image, or it just?
This one?
No, the another one. The cluster feedback. The one that you had. Yes, the one.
Okay. Well, no. So the radio jet it's this here. So it's more or less. It's not lined up with us, for instance. I'm not sure exactly what the orientation is, but it's a decent amount in the plane of the sky.
All right.
And the thing is, that if you line up the contours, they line up very well with this sort of gap. So they really are sort of pushing it out. And you can also measure the pressure inside of this based on the electrons and everything, and do energetics to see how much energy this is actually dumping into the intercluster medium. It's a significant amount.
Thank you.
Hi. Guess I missed something because I didn't get it why low mass black holes, in case AGN black holes
Vary more than
vary to the variability of the high variability, low mass, high variability, and vice versa.
So I think the easiest way to think about it is if you remember that the radius scales with the black hole mass, and inversely, right? So a bigger black hole mass will have a larger inner stable orbit. And so you can think of, you have a bigger disk versus a smaller black hole will have a smaller disk. And so then the variation timescales can be quicker, and that may allow the sort of stochasticity to be larger. But the exact reasons why is maybe not super well understood. I think there are some theories about it, but we haven't really nailed down one yet.
And it's a simple question, but the build involve sorry, the bulge evolved by turned on AGN means that it's a newborn galaxy, or no?
It's a newborn.
And because before that we have the mixed galaxies and the AGN is not turned on. And after that, the bulge evolved and...
Well, the idea is actually that well, as we'll see a little bit later in the next couple lectures, the AGN is kind of turning on and off constantly.
Okay.
And so every time there's some gas, which you would use to build stars in the bulge, some of that gas gets driven down into the central region, into the supermassive black hole, and feeds that. And so you ideally should kind of grow them, not simultaneously, but they both will grow whenever you dump a bunch of gas onto the galaxy to form new stars. And in that process, when the AGN turns on, the idea is that it will impart some energy back into the gas to sort of halt star formation from going wild. But seeing that actually happen has been pretty tricky, because the scales, you have to measure it on lots of different scales, and we don't have good examples in our galaxy to do that with.
Thank you.
Yeah.
Hi, I don't understand surely the time scale of the variability of a supermassive black hole is longer, or they vary less? I'm not
They
sure.
vary less, is what it is. It's not that
Intrinsically.
right. So the fluctuations are smaller. So it's still varying. They're still varying constantly, but the sort of scale of that variability, should go. Basically, the longer you wait, the larger the fluctuations will be. But then the overall sort of amplitude of those is linked to the black hole mass or to the accretion rate, as we've seen. And we basically have to come up with a disk model that explains that.
Thank you.
Other questions?
You showed near the start that the variability over time of the emissions of the AGNs are different for different wavelengths, for different bands, and they are for higher wavelengths, right? Is it understood why that is, and also is it
Or higher for shorter wavelengths?
yeah, sorry, higher for shorter wavelengths, and is it understood, and also is it in some way proportionate to the amount of light that is emitted in different wavelengths?
In some sense, yes. This is sort of understood in the sense of trying to come up with a model of reprocessing. Now that is a model. It isn't necessarily the standard that everyone sort of believes. There's problems with it, and there's sort of tests to try and improve it. It's sort of a working model. With regard to then scaling this by luminosity, I think, yes, I think there will be some scaling, and I'm trying to remember if I have that at all. Right, so I think, and there's a maybe mild trends in all of these that are different, and so there might be some modification, but it's pretty hard to see it in here, so I don't have anything to actually show, but I think there should be a coupling between that. Yeah.
ask a quick question. You showed the molecular outflows in the last few slides. Is there evidence of star formation? Can these outflows, can star formation be triggered in these outflows?
Yes, so there's some evidence that they can trigger it, not widespread at all, I would say. Again, it's still pretty unclear because we don't have really good spatial resolution for any of this. And so, for instance, in some jets, radio jets, they tend to see some shocks that are going on at the edges of the radio jet, which might actually think about making the momentum sort of more isotropic, or sort of shedding some of the energy from the jet, the mechanical energy outward. And then there's the possibility that the jet can move clouds and make stars collapse. So certainly there's indirect evidence for that, I would say, not strong direct evidence, but suggestive evidence that, okay, there's star formation near a jet. Is the jet responsible or not? It's difficult to say. But it's certainly possible.
Any more questions? So thanks, Franz, again. And we have Gustavo just wants to say.
Gente, eu vou falar em português. Então, sumiram 3 laptops e uma mochila. A gente já olhou o vídeo, então a gente